We propose Beacon3D, a novel benchmark and evaluation protocol for 3D vision language, grounding, and question-answering tasks. Beacon3D is built on 30 meticulously selected high-quality real 3D scenes. Seeing understanding necessitates project understanding. We go through all object instances in each scene for evaluation. Take this chair, for example. Now, we evaluate the understanding of this chair. In the grounding task, the model is required to find the target object given a referential text. Though the model correctly grounds this text, it doesn't necessarily mean it understands the target object. Our object-centric evaluation designs multiple tests per object with diverse language variations to manifest the true model capability. The texts involve various knowledge types such as appearance, geometry, and spatial relations. Here, the model passes the first two tests but fails the third test. Next will be the metrics. While previous per-case metrics simply average the accuracy of all predictions, our object-centric metrics consider per-object accuracy. The model succeeds only if it passes all three tests. Similarly, we have 3 questions per object for the KA task. Here, the first question asks about the object above the target chair, which concerns spatial relation and class identification. The second question queries the color of the target chair, which concerns appearance. The third question asks about the distance between the trash can and the target chair, which focuses on spatial relation. Still, 2 correct out of 3 tests yields 0 accuracy under object-centric metrics. The test data of Beacon3D is organized in a chain structure. In grounding chain, the question directly uses one grounding text to refer to the target object, which connects the 2 tasks and accommodates chain analysis. Then, we categorize the model's performance into different types. We say the model has a good grounding coherence if both grounding and QA are correct. In particular, we identify 2 types of broken grounding, QA coherence. Type 1 refers to correct grounding and incorrect QA, indicating a lack of QA skills. Type 2 refers to incorrect grounding and correct QA, indicating shortcut and overfitting. To quantify the 2 types of broken coherence, we define 2 metrics. R1 denotes how many QA failures come from type 1 broken, which is close to 50% for current 3D vision language models, suggesting a significant task intrinsic gap between grounding and QA. Auto denotes how many QA successes come from type 2 broken, which is also close to 50%, suggesting severe overfitting in QA. Given the significant role of grounding, we also construct grounding chain with coarse-to-fine grounding texts to assess models' performance coherence across different granularities. For example, there are 7 chairs in this room. Only 2 chairs are next to the corner table. And the target chair can be distinguished by its gray color. Similarly, each grounding chain starts from a simple text, then it evolves with incremental complexity highlighted by yellow and purple to filter the target object candidates, and finally it converges to the unique target object. Such a coarse-to-fine scheme helps identify the boundary of grounding capabilities. The performance across the coarse-to-fine grounding chains can be categorized into 4 types. We show the proportions here, which indicates that grounding fine-grained texts is more challenging than coarse texts, and grounding fine-grained texts is particularly challenging when failing in coarse texts. Given that grounding fine-grained text is crucial to guarantee solid QA performance, our chain analysis suggests the need to improve 3D vision language models in complex text grounding and grounding QA coherence. Thanks for your attention. We proposed a novel benchmark, Beacon3D, for 3D vision language understanding. We hope Beacon3D could benefit the 3D vision language community towards faithful developments.